Hi guys. Alright, so this is a walkthrough for the Toying with Energy Lab. You should have been sent home with a little popper guy. Right, yours is either going to be blue or yellow or pink or green. Alright, so mine's purple. And you should be able to flip it inside out and then set it on a surface. Now, when you flip this guy inside out, you're doing work on it. Right? You are putting energy in the system. Before you flipped it inside out, if you just set it on the table, nothing's going to happen. It's just going to sit there. But when you flipped it and set it on the table and did work on it, and work is how we add or subtract energy to a system, you actually add potential elastic energy to that system. Alright, so now this popper has potential elastic energy. When it pops, it shoots off of the table, and you actually have the energy converted into kinetic energy. So all of the potential elastic energy, all the work that you put into the popper, becomes kinetic energy. Now, as the kinetic energy gets less and less and less because the velocity is slowing down, it's getting higher in the air, your kinetic energy is decreasing, but your potential energy is increasing, and at the very top, at your maximum height, it's all potential energy. Now what's going on here, and we know about the conservation of energy. The conservation of energy equation is, let me pick a different color here, the total amount of energy that we had before, plus or minus any work that we did, is the total amount of energy that we have afterwards. So at first, if the popper is just sitting there, hanging out, you haven't done anything to it, you actually have no energy before. But then you do positive work to it, you flip it inside out, and now you have positive work, which becomes potential elastic energy afterwards. That's the first conservation of energy equation. Then you would have potential elastic energy to begin with, and when it pops, there's actually no work because the energy is just being transferred, and it's being transferred into this kinetic energy here. And then you have kinetic energy before, and it's just being transferred. At the end, you have all potential energy. Okay, so what the first section of the lab asks you to do is just write down your thoughts about what is going on here. As the popper flies into the air, how is the energy changing? Just talk to me about transfer of energy, if there's any work going on, if the energy is just being transferred, just talk to me. Alright, so then the next couple of questions, I believe they ask, what is the equation for potential energy? And we know that that is mass times gravity times height. And what's the equation for kinetic energy? And we know that kinetic energy is 1/2 mass velocity squared. Okay, so we know, because of conservation of energy, we know from here to here, after we put this initial work in, the energy just is transferred. We're not adding or subtracting energy from the system. So all of the kinetic energy that we have right here is equal to all of the potential we have right here. So we know that the kinetic energy here, when it's all kinetic, is the same as the potential energy when it's all potential. So we can actually set these two equal to each other. So, let's pick a new color. There we go. We can actually say that mass times gravity times height is equal to 1/2 mv squared. Now, we don't know the mass of our popper. Now, I guess you could take the mass of the popper, but if you look here, we have mass on the left side and mass on the right. Say I were to take this mass here and I wanted to put it on this side, and we were to divide both sides by mass. What happens? And just cancel out. So what you end up with is gravity times height equals 1/2 v squared. And then you would just plug in everything you know. We know that gravity is 10. Height, now you're going to measure your own height here. So hopefully, and you measure it you'll probably initially measure it in centimeters, but you need to convert it to meters. Alright, so see how high your popper flies, and then mark that place and measure up to it. Like put a piece of tape on the wall and then measure how many meters up. So my particular example is going to be 1.3 meters in the air. You're going to have something a little bit different probably. So you can say your height is 1.3 meters, and that is equal to 1/2 your velocity squared. And I believe the next section of the lab asks for you to solve for that velocity. So 10 times 1.3 is 13. Let's go ahead and double check that. 10 times 1.3 is 13. So 13 equals 1/2 velocity squared. So if we were to divide both sides by 1/2, which is the same as multiplying 13 by 2, we would get 26 equals v squared. So in order to find velocity, we would have to take the square root of both of those, and our velocity is equal to the square root of 26, which is 5.1 meters per second. Alright, so you should have somewhere between 4.5 meters per second and 5.5 meters per second. My particular one says 5.1. So we have a height of 1.3 meters, our gravity is 10, and we can solve for that velocity, and I got 5.1 meters. Alright, and then I believe the next section asks a few things about what's going on here, but from a kinematic equation perspective. So what you need to do is back up all of this, everything that we know, with the kinematic equation. So we know right when it snaps off the table, we have an initial velocity. Alright, and that initial velocity is actually what we calculated here. The velocity right when it snaps off the table, this kinetic energy right at the very beginning, is including that velocity at the very beginning. And then this velocity at maximum height is going to be our VF, alright, and our VF is actually going to be equal to 0 meters per second at maximum height. It stops for just an instant before it starts falling back down. So we know our final velocity is 0 meters per second. Our initial velocity is 5.1 meters per second. We know that acceleration is, you can either use negative 9.8 or negative 10. I'm going to use negative 10 this time. And we have two other variables. Time we don't use at all, so we can cross that out. And then we also have delta y, and our delta y is what we're trying to figure out with our kinematic equation. Now when we plug all this in, we should get pretty close to the height that we measured here. So we're going to use the equation without time because we have all the other variables and we need delta y, and it doesn't ask us to solve for time, it doesn't provide time, so we don't use time. You're going to use the equation VF squared equals VI squared plus 2a delta y. And then you plug in all of your variables. Our final velocity is 0, and 0 squared is still 0. And then you're going to get your initial velocity squared, so 5.1 squared, plus 2 times negative 10 times this delta y that we're trying to solve for. Alright, so 5.1 squared is 26. So we end up with 0 equals 26 plus 2 times negative 10 is negative 20 delta y. Alright, so these two are stuck together. Right now we have to subtract 26 from both sides in order to get to our next step. So we end up with negative 26 equals negative 20 delta y. And then we would just divide both sides by negative 20 to get our delta y. Negative 20 over negative 20 cancels out. Negative 26 over negative 20 is equal to, oh my goodness, 1.3 meters. Ta-da! That is remarkably similar to the height that we measured. Alright, so what this tells us is that our kinematic equations and our energy equations are related, and the popper here is a projectile. This is an example of projectile motion. Okay?